So I had a question about if you add a pure solid or liquid. If you add a pure solid or liquid, does that impact the equilibrium? In general, no, but there are exceptions. So the exceptions would be trick questions. So for example, let's say you had this equilibrium, right? In this equilibrium you had this chromium 3 and some tin 2 or something like this, right? In equilibrium with chromium 2 and tin 4. And so, you know, in this, if we add a pure solid, let's say I add some chromium 3 chloride, solid, will that impact this equilibrium? Yeah, because here the chromium 3 solid will dissolve and increase the chromium 3 concentration, pushing the equilibrium to the right. And so it depends, you know, if this were solid chromium metal and I added some more solid chromium metal, the activity doesn't change, then you're okay. You know, or the other thing is, what happens if I add water to this, a pure liquid? Well, if I add water to this, this would be a trick question too, because what will water do, adding water to this? It will dilute all the species, right? Now, it just so happens we have three aqueous species, three aqueous species. So in this case, it's balanced. It doesn't favor one side or the other. But, you know, if it wasn't balanced, that is, let's say you had something like this, you know, and I add pure water, what would happen to this? This one you should be able to think of intuitively without even thinking about Le Chatelier's principle. Basically, what we're trying to do is we're trying to dissolve calcium carbonate. The more water you add, the more you should be able to dissolve. So this, adding water to this is actually going to shift it to the right, because it's going to make it more dilute, and it's no longer, Q is no longer going to equal K, and that kind of stuff. What happens if I add solid calcium carbonate to this? Nothing's going to happen. It's already saturated. You can't dissolve anymore. You've hit the max, right? And so when somebody says, like, you know, when you add pure solids or pure liquids, yes, there's no impact unless it's a trick question like this, you know, where it does impact something else, you know? And so you have to think one step further in this, and that is, what impact would adding calcium carbonate have to this? Nothing. It's pure calcium carbonate. But if you added pure water to this, hey, water has an activity of 1, but we aren't looking at water. You know, there's no water in this equilibrium, except other than the solvent here, and adding more solvent is going to screw up your concentrations.
So when water is part of the equilibrium, then it wouldn't?
Yeah, if water is part of the equilibrium, then it wouldn't have any impact. So for example, if you had something like this, where CO2 plus H2O liquid yields carbonic acid. You're looking at this equilibrium here. Adding more water, is that going to change the... This is CO2 gas. This is aqueous. Would adding more water change the activity of water? No, but adding more water could potentially change the concentration of dissolved carbonic acid, right, screwing it up. And so, unfortunately, you know, what we have to do is we have to tailor the questions to avoid this kind of problem, unless you want it nice. If you want something nice and clean, You know, something nice and clean would be where we'd have something like this. This is nice and clean, right? Because here it's nice and clean because if you add water, the only thing it's going to impact is H2O liquid. Is it going to have any impact on these gases? No, so this works out very nicely because you add more water, is that going to shift it in any direction? No, its activity is the same. It's still pure water, right? This is not nice and clean, right? And so what we could do, it depends on how messy you want to get. You know, we could just restrict the type of questions I ask. I restrict the type of questions I ask so that it always works, you know. When you add a pure solid or pure liquid, it has no impact. Or I can make it a little bit messy and, you know, it depends. And so usually you have both types of questions in there. You have the questions where it kind of works out nicely and the questions where it's a trick question, maybe advanced questions that people who have, you know, and this is not something that's easy because people memorize this rule, like say last night, you know, pure liquids, pure solids shouldn't have an impact. But people who've been thinking about it for a while, you know, they'll think, is that, you know, and so I kept it simple, you know, usually. Try to keep it, you know, doesn't have any. Adding calcium carbonate to this, no impact. Okay. But it's not to say that, you know, when you leave this class, you know, things get easier. No, things get more complex because you're supposed to have all those neurons connected so that you can deal with the more complex issues. All right, so yes, in general, yes, solids and liquids do not impact the equilibrium. Okay. All right, other questions? Okay. Number 15 on the practice test. Can you read it out, or somebody read it out for me?
So, 0.100 moles of
0.100, so 0.100? Okay, 0.100 moles of acetic acid?
It's like H and then AC. AC was active.
Oh yeah, you know what? AC's not. I'm sorry. I just did it.
I thought it was.
You know, each semester I teach because I forget what I talk about, and sometimes I get stuck going in one particular direction. So this semester I was stuck doing ammonia. Usually when I do weak, I do acetic acid, and I do a lot of examples of acetic acid. And so acetic acid gets very tiring to write. You know, HC2H3O2. And so what people do is they just abbreviate this AC minus, and this is H plus. And so acetate is AC minus, HAC would be acetic acid. And so even though there's an AC here, but it's a metal,
I know, it's like
you would be thinking metal hydride, you know, or something like that. But I'm sorry, that was supposed to be acetic acid, and that semester, what was it, in 2013, I did a bunch of examples of acetic acid. And so then pretty soon I just said, okay, let's not write this, let's just use the abbreviation here. This is standard abbreviation for acetic acid. So if you Google it or something, you'll see. HAC is acetic acid. Okay, since I did so many examples of this, you know, the Kc value is 1.8 times 10 to the minus 5. And I just forgot to write it there because we did like 4 examples of acetic acid, but I wrote it on the board. You know, sometimes you're going to see information missing, but usually, like a lot of the K values, I'll write on the board to take up less space. But if I can fit the K value in there easily, I'll put it in there. But if it takes up another line, I might write it on the board instead. Okay. Okay. Yeah, it would have been given. Otherwise, you wouldn't have been able to come up with quantitative answer. Okay, well, what else do you have questions with?
Well, there was one that, number 11, it says, which describes best the activity of a gas. And I put real pressure, but I wasn't completely confident.
It's like in the book it says it's based on, like it's closer on the real gas, pressure, right?
Yeah, I put real pressure, but
In the book, it said it's based on.
It said like activities help you get closer pressure than the ideal pressure.
Yeah. Okay. Well, you know what the activity is for solutions. This activity is AKA the effective concentration. The effective concentration, is that more realistic than the ideal concentration? Yeah, and so we call that the real concentration. The analogy I used for activities was, it's like the van der Waals equation for real gases versus the ideal gas law. You know, which one is going to be more accurate? Always the van der Waals, you know. But sometimes we can make do with a simpler ideal gas law because it just saves us a lot of time. And so the answer to that was the activity should be the real gas pressure. Real gas pressure, corrected. And so for ideal gas, you just use the ideal gas law equation. For real gases, you would factor in the intermolecular forces and the volume of the particle to get the real gas pressure. Okay. There, it's not so difficult. We could calculate the real gas pressure just using the van der Waals equation, right? But what about aqueous solutions? You know, what's the equation for determining the real concentration? Well, if you go back into chapter 13, you'll see we'll need like a gamma, you know. Now, how do we get the gamma, the activity coefficient? Those things. Did it show you how to get the activity coefficient to calculate the activities for solutions? No, and so that's one of the things we're just going to skip in this particular semester because it's beyond, we'll just say it's beyond the scope of this class. In the very next class, if you continue with solutions, which a lot of you will, because, you know, even you biology majors are going to be hit with this. You're going to have to deal with this because so many biological things happen in aqueous. In fact, water in biochemistry, they spend one whole chapter talking about water because water's so so important to life. And so then you deal with those types of things later. And so the next class for bio, and of course for engineers too. That's all called thermodynamics. This activity stuff. Okay, what else? You guys have homework or whatever else?
Number 10, it says which is expected to have an activity of 1, and I put silver iodine, but I wasn't sure.
What were the choices for number 10?
Hydrogen, oxygen, water, carbon.
Okay, hydrogen. You know, hydrogen's close to ideal, but it's not the closest to ideal. What is the closest gas to ideal? Helium. But even helium isn't ideal because what happens to helium at 4 Kelvin? It liquefies. And so helium's not an ideal gas. You know, ideal gases stay gases until 0 Kelvin. And so, yeah, hydrogen, you know, that doesn't necessarily have an activity of 1 because it's a gas, right? It's a gas. So its activity is going to depend on its pressure and its real pressure. What else were the choices for that?
Oxygen, water.
Oxygen, gas, water, liquid.
Water.
Oh, water was in the gas state? Okay, that's a gas too. Water is the least ideal of those.
Carbon as a gas.
Carbon's a gas.
And then
Silver iodide is a solid, so silver iodide.
That's right.
Yeah.
But I wasn't sure like.
Well, the thing is, does the concentration of silver iodide change by adding more or taking? No, it stays the same because it's just pure silver iodide. And so even if you add another bucket full of silver iodide, as long as it's pure, its activity is not going to change. What changes activities is changing the concentration. And so you have to pack in more silver iodide ions in there or make more void space. That's not going to happen because it's a crystal lattice. Okay, any other questions? Matthew?
Looking at number 12.
Uh-huh.
Which solution below is expected to behave least ideally, and they have 6 moles of hydrochloric acid and 0.100 moles of hydrobromic.
All right, so the question is, which is expected to behave least ideally? Solution. 6 molar HCl or 0.1 molar HBr?
Yeah.
ACL.
6 molar HCl because ion pair interactions. Ion pair. And ion pair interactions, why? Why are ion pair interactions more significant for HCl versus HBr?
ACL is
The higher the concentration, the more the more probability that the higher the probability that they're going to be close enough to have pairing interactions.
wouldn't also like chlorine be more electro negative?
Not chlorine,
I mean chlorine.
Chloride is not so electronegative.
But compared to like, because that's also what I thought. Like the size of it.
I know, but the explanation isn't quite
Isn't
right. You wouldn't invoke electronegativity here. It already has an electron. Why does it want another electron? Right? It already has a negative charge. So you wouldn't talk about electronegativity of chloride versus bromide. You would talk about
concentration.
We just talked about concentration effect. It's a different kind of concentration, though. You would talk about ion pairing depends on 2 things. This should be automatic. What 2 things come? Does it depend on? This is why I say review. It's not like being a genius and being able to come up with this stuff. It's just content recall.
How negatively charged? Concentration.
Concentration of charge or charge density. Right? Chloride has a higher charge density, so not only is it higher concentration, but it has a higher charge density, which is going to...
That's what I was trying to say.
Yeah, I know that's what you're trying to say, but I often hear people talk about electronegativity, but it's not. No, it's a charge. It's what we call an ion-ion attraction. An ion-ion attraction, you don't invoke electronegativity in that because it's not pulling electrons from the cation. Chloride's not pulling electrons from the cation. If it was electronegativity, then chloride would want to pair up with bromide, right? Because chloride would want more electron density, so don't talk about electronegativity there. It's going to be ion attraction and charge density.
So if they were both 0.100 molar, it would be HCl.
Yes. Right. So the question is, if they're both 0.100 molar, for sure it'd be HCl. Okay. Charge density.
I know you kind of went over like the H2O, like if you add the liquid to that hydrogen or oxygen or H2O.
Yeah.
But on your practice exam, you have kind of like the same thing, but you have 1/2 oxygen gas. Like would that affect it? Still, if you added liquid hydrogen?
No, it wouldn't affect it at all. It changed the K value, right?
Yeah.
If it were 1/2, the K would be the 1/2 the K value or the square root the K value? Square root, yeah. But otherwise, you know, you reach this equilibrium, it's going to, it's not going to impact it. Yeah. So fractions are very common to. It's not going to impact. Still, H2O liquid, it doesn't change its activity.
When is chapter 16?
Chapter 16 test is supposed to be next week. I think on Thursday of next week. Then you'll have a little bit longer break, you know, because chapter 17 is kind of a long chapter and I'm behind schedule. So chapter 17 is likely not to be the following week. Do you like this schedule, or do you want to switch to midterms? Too early to decide. Yeah, 16 has a lot of homework. I was looking at it.
So you're gonna cut that down to like
17 has a lot of homework too, doesn't it? 16 had the most homework. 16 has a lot of homework. You have the solutions guide. Use it. Then you have you know what you have in your homework notebook is you have a bunch of worked out examples you can review. That's it. No, sorry.
Do you grade it first?
Yeah, the first exam I'm going to hand back on Thursday.
What about the quizzes? There are like 2 quizzes.
Yeah, I have 2 quizzes. This, you know, that quiz I gave with the silver and the nitric acid and the hydrochloric acid, I think, was that it?
And there was one before.
That quiz, you know, I'm going to do something with that quiz because a lot of people got it wrong. And so that particular quiz, you know, and there shouldn't be any reason to get it wrong because all you're doing is you're following a set of rules, right? And the set of rules is like step 1. What you do, you know, you don't have to think about it. You just, you know, step 1, do this. Step 2, do this. And so you just go through the steps. You don't have to have anything memorized because you have the charts. Okay? So it's just this is why I call it the chart method, because all you do is look up the stuff in the chart. Now if the stuff is not in the chart, then it's a bit more challenging. And so on the practice sheet I gave for the reactions, you know, that reactions homework sheet, there's stuff not on the chart, you know, you got to figure out, you know. But you know, on this last one, everything was on the chart, and so, you know, and I think people because well, the Chem 1A veterans have had it, but maybe some of the newer people, you know, it depends on what the Chem 1A instructor likes to emphasize, you know. And so I'm going to give a second chance for that. And for the people who got it all right, I'm either going to give it today or Thursday. And then for the people who got it all right, 5 points, I'll just give you a bonus. So what you can do is you can earn half the points that you lost back by redoing it. And if it's right, then I'll give you half the points you lost. If you did it all right, then you don't have to do anything. I'll give you. You want to do that today? Thursday.
Can you give it back to me?
Yeah, we'll wait till Thursday. How about that? All right, if there are no other questions, we can talk about the lab. If some other questions come up, just go ahead and stop me. But we're going to work on a qualitative analysis starting Thursday. And qualitative analysis, we're breaking up into parts. So what you do is when you prep your notebook, you just kind of see, you know, I think I can make it this far. And that's how far you'll prep. You don't have to prep the whole thing because it's a very long experiment. And so just break it out day by day. The way it's going to work, though, is, you know, you want to get through the known as quickly as possible, but then again, you want to be as thorough as possible because all you're going to work with are your observations. And so when we prep our notebook, we'll keep this in mind. There are different ways you can prep the notebook. So we're going to start just with the cation analysis. The cations, there's 10 cations. 2 of these we do individual tests for. And so we have an unknown sample and a known sample. And so we're going to start off with a known with 10 cations. They're all AQ. This kind of gives you an idea what the anion must be. You know, it's got to be a highly soluble anion, like what? Sulfate, nitrate. What are the most soluble anions? Nitrate, acetates, and chlorates. Good. Except, you know, the situation is nitrates are quite soluble in terms of metathesis reactions, but nitrates are kind of reactive in terms of redox reactions. So we have to be careful there. You know, if we're looking at metathesis versus redox, because sodium nitrate, very unreactive, metathesis. Sodium nitrate, potentially reactive, redox. Could be very reactive, redox. Acid base, nothing. And so what we're going to do is we're going to separate it into 3 samples. One, we're going to test for ammonium. Another, we're going to test for sodium. These are individual tests. Individual tests are short, and these can be done last. For the other 8 cations, we're going to do the qualitative analysis scheme, similar to what you might have done in Chem 4. And what that means is it's a long sequence of separation and conformation, right? So you want to separate out, that is, the mixture into of individual ions, and then confirm the presence. So the first separation that we do is adding what? Yeah, and so what I do is, for prep, I just say, you know, how many mils do you want of this known sample? Yeah, the known sample. How many mils of this do you want to start? In fact, what does it say in the procedure? Can somebody just read the procedure and say, you know, you'll see the procedure. You'll notice what the procedure is by looking for something that gives volumes. You know, most of it is just talking about the reactions, right? Right before the report sheet. Did somebody find it? Can somebody tell me what the first part of the procedure is? Just read it out loud for those who don't have it.
Basically says adding enough to completely precipitate silver iron.
All right, but what before that? Add enough what to what? What are we adding to what?
Hydrochloric acid to the solution.
All right, we're adding hydrochloric acid. How much hydrochloric acid and what is its concentration? 6 molar hydrochloric. And it will have, what does it say?
2 drops.
2 drops. But the thing about the amounts is the amounts are just a rough estimate. We don't want rough estimates in our procedure. When we write our observations, we want an accurate accounting for how many drops it takes. So let's say I add 1 drop, nothing happens. What should I do? Add another drop, right? Add another drop. Still nothing happens. What should I do? Add another drop. If I'm on the 50th, 60th drop, then maybe something's wrong, huh? But hopefully before you get to the 50th, 60th drop, you'll think something must be wrong, because if I add the 5th drop and still nothing's happening, then maybe nothing's going to happen, right? Maybe I better stop. But sometimes 2 drops is not enough. Let's say I add 1 drop, I get a precipitate, a white precipitate. Should I stop or keep going? I need to keep going. So I add 2 drops. Looks like nothing has happened. Should I keep going? No. Keep going. I need to keep going until I get the maximum amount of precipitate. But sometimes the solution is so cloudy, you can't even tell. You know, you're adding a drop into a fog of precipitate, and it's so hard to tell if you're getting more precipitate or not. Well, what do you do? Huh?
Heat it up.
You could heat it up and try to do what? What's that called again?
Accelerate.
Heating it up will promote what? Will promote collisions, which helps do what? And what's it called? Coagulate. Good. That's good. Digest or coagulate. Those are vocabulary terms from Chem 1A. So you could try digesting it by heating it up. It doesn't take long to heat up a test tube. You got a test tube clamp, you got a burner. Or, yeah, there's that machine, that round machine there. Do you know what that round machine is? It's a centrifuge. And so this is what we do. When it starts to get too cloudy and you can't see anything, then you get a blank test tube, which is just a matching test tube as a counterweight. Fill it with some water. Take the 2 test tubes to the centrifuge. You got to be careful because we have different centrifuges for different sized tubes. And so make sure your tube fits in there properly, because some of these are for the big tubes, some are for the small tubes.
Would the speed matter? How fast?
No, the speed matters. You know, you want it to be quick. So all you do is there's a timer on there. So you just turn on the timer and then listen. Once it hits maximum speed, turn off the timer. And then you have 2 choices. You can just wait until it stops, or you can break it. They have a little black collar on here. You can break. So here. So I just turn it on. If it starts to rock violently, then it's not balanced. And so just listen. And then it's hit, let's say, maximum RPM, and then just turn off this. And if you don't want to wait, you could break this with a paper towel or a piece of paper, but don't bring it to an abrupt stop. If you bring it to an abrupt stop, you might dislodge the precipitate at the bottom. And so let it come to a gentle stop. Okay, if you just wait here, it's going to take a long time, so everybody breaks. And then just a gentle stop, and then you're done. I'm sorry? Yeah, you want to put 2 test tubes opposite each other, so it's balanced. If you only put 1 test tube in there, it's going to make an awful noise and start rocking. And so we need a counterbalance here.
So is that doing the same thing as heating it up? Like
No.
getting up?
No, heating it up makes the particles bigger, the precipitate bigger.
Yeah.
All this does is it compacts the precipitate to the bottom.
Compressing it?
Right, and so what the precipitate's more dense. It'll go to the bottom. It just makes it settle a lot faster. Now, when the precipitate's at the bottom, it's easy to tell. You add a drop and look for cloudiness. If there's cloudiness, what do? You got to keep adding until you don't see any more cloudiness. Why is that so important? Why do we have to make sure we get complete precipitation? Right. We need to trap all the cations because we want to trap all the cations that precipitate over into the precipitate, because if we don't trap all of them, some of the cations escape into the solution and screw up all your subsequent reactions, because one of the cations we're trying to trap is silver ions. If those silver ions get past and over here, then you're going to be looking at weird oddball colors, and you're going to be coming up to me saying, what's going on with this? It's such a weird, and then I'll figure, wow, probably incomplete separation. We need to do every single separation completely. Otherwise, we have something called interfering, or reactions or interferences. And we have to eliminate those interferences. Okay. All right, so what we've done is we maximize. So this 2 drops, I always completely ignore it because I'm always trying to maximize, right? But the thing is, you want some idea actually how many drops it really took. And so what we do is you could have the 2 drops there and then just write, it really took 8 drops to completely do it, or something like that. And so you have some kind of reference point for the future when you repeat this. And so normally what a lot of people do is they'll write the flow chart in one color and their observations in a different color so that they can see. And then what they'll get is, let's say, a white PPT. And so what is this white PPT? Look at the flow chart with me. For this lab, I just prep flow chart. I don't do anything more. I just make a little flow chart or over multiple pages so I can see what I need to do in each step, each separation step. It should be silver chloride. And so we know that HCl and silver ions like each other, right? In fact, chloride loves silver ions. And out of all the cations in there, if we had lead, what would happen? Lead would precipitate. If we had mercury 1, it would precipitate, right? But we don't have any lead and we don't have any mercury because we used to have lead and mercury. But yeah, now we only have one heavy metal in here, and that's silver. Silver is considered a heavy metal, but not as bad as lead and mercury. Well, maybe even worse sometimes because silver. You don't want to touch. You don't want to. An easy way to check for silver ion: dip your finger in there. If you dip your finger and it comes out black and it doesn't wash off, then you know you have silver in there because the silver is a powerful oxidizer and it'll oxidize your skin and precipitate out tiny crystals of silver, which you can't wash off for a week. So in this, we used to do the complicated version of this, and so I had one student with silver stains all over her hands, and she said, "I can't. I've been washing 30 minutes. I can't wash this off. I got an important job interview right after the class." Yeah, she was very upset. I had gloves that semester too. But, some people don't like gloves because their hands get sweaty and stuff. Nitrile gloves are better than latex gloves. But you might as well get used to wearing gloves because now it's required in most places. So. All right, but how do we know that's silver and not lead and mercury? Well, one way we know is because you have no lead and mercury in here. Another way is we test the precipitate, because silver chloride has different chemical reactions than lead chloride, which has different chemical reactions than mercury chloride. I should say lead 2 chloride and mercury 1 chloride. And so we don't stop here because this doesn't really nail it down. If there was a chance that this got contaminated with lead or mercury, then we're uncertain. And so what are some of the chemical properties of silver chloride versus lead chloride versus mercury chloride. This is not apparent because our lab manual is not written this way, but you know, we get this white precipitate. Now the thing with this white precipitate is this. We have to make sure we completely separate it from the solution, because the solution is going to contain the remaining ions. The remaining ions better be over here. Well, contamination goes both ways. One, how likely is it that my precipitate is contaminated with the remaining ions? You know, this is surface contamination, you know, wet with a salt solution containing, very likely, right? Very likely. And so what I need to do is I need to make sure that I wash my precipitate. You always wash your precipitates. But this is the trick. When you wash your precipitates, they're for sure going to be contaminated, right? And so your first wash, what do? Do you throw it away? Your first wash you never throw away. Because if you throw away your first wash, you're losing a lot of ions. And so your first wash you include over here. But by your second and your third wash, you have to make a compromise. On the one hand, your second and third wash will contain some ions. But your second and third wash, if you add it over here, you're going to make it everything more dilute and more difficult to test, right? We don't want to over dilution, because what's the cure for over dilution? The cure for over dilution is you have to boil off the water in one of the hot plates, which takes time. Not that much time, but it's just an extra step you have to do. And so you could add your second and third wash here and then boil down the solution to make it more concentrated. Or what we do is we just toss the second and third wash into waste. Sometimes we'll keep the second wash depending on how concentrated it is. But whatever, if there are ions over here that aren't silver, those are going to screw up the subsequent reaction. And so do you see, in this procedure is not about being perfect. I mixed 2 drops perfectly in here. You know, I washed it perfectly with this. You know, it's not you're always adjusting the amounts to compensate. You know, your known should have everything, right? Your known should have everything, but your unknown, will it have everything? No, it's not. And so I have people over here trying to wash an invisible precipitate. They didn't get any precipitate because they didn't have any silver ions, but they're still trying to wash it. And so they come up to me and ask me about it, but I tell them, you know, I can't say anything because this is all based on your lab notebook. And so you'll have to sit there and figure it out, or go home and figure it out, right? After lab. And so, yeah, and then they keep adding, you know. 60 drops hydrochloric. 60 drops of hydrochloric means in the very next step, they're going to be adding a lot of base to neutralize that. Pretty soon, they switch from test tubes to beakers, bigger beakers. And this is just at the start, and then I'm thinking, oh no, this is not looking good. It's looking very bad. Usually they'll can the experiment and start over. But you don't want to do that. Like if you're on step 50, down here, you don't want to can it and start all the way over, because you can't back up. Sometimes you can back up, but most of the time it's hard to back up a few steps and redo those. Most of the time it's going back to the beginning, and then, because each of these separations is key. But for your known, you know, it's not as bad as it might think. A lot of people are able to run their known once and their unknown like two times, or even 3 times, depending on how many ions they have, how quick they are. All right, what do we do to this white precipitate? This white precipitate should be silver chloride solid. The reaction here, sometimes it helps to write the reaction. Silver ions and chlorides, precipitate and silver chloride. What do we do next?
Add ammonia.
Add ammonia. If you add way more acid than you need, then the ammonia is a base, and you gotta, if you added way too much acid, you gotta add way too much ammonia base, because you gotta neutralize all that excess acid that you might have dumped in there. Although, you know what? That excess acid should have been washed out anyway. And so over here you'll see we're going to be adding a lot of excess base to neutralize the excess acid. But anyway, we add ammonia. Now here we want to add the ammonia straight to the precipitate. So here it's best to have no solution. You know, the precipitate as dry as possible, which is impossible because you aren't going to be drying these things. It's going to be slightly wet with DI water. And you add the ammonia, what should the ammonia do? How many drops of ammonia and what molarity?
Four drops of 6 molar.
4 drops of 6 molar ammonia? Okay, so we want to say 6 molar ammonia, and then over here, 4 drops as a guideline, but are you really going to pay attention to that number? No. You don't pay any attention. What are you trying to do at this step? You're trying to dissolve the precipitate. You know what kind of reaction this is? This is a Lewis acid-base reaction. We want to form this and this. All right? And so we get an aqueous solution. And so the purpose of this is precipitate dissolves. So if the precipitate dissolves with 1 drop of ammonia, are you going to add the remaining 3? No. If the precipitate drops with dissolves with 1 drop of ammonia, do not add 3 more drops.
What about one? Just to finish. One more drop.
If the purpose is to dissolve the precipitate and it dissolves in 1 drop, there's no reason to add 1 more. 1 more, you're just hurting yourself. You're hurting yourself. If the precipitate doesn't completely dissolve in 4 drops, then you better add more. The thing is, what also helps? I see this, people just adding drops, but they don't do anything else. What helps to dissolve the crystals? Stirring it or crushing the crystals with a stir rod. Right? That helps to dissolve it. And so you want to do those things in order to use a minimum of ammonia. Because if you add too much ammonia, the next step doesn't work. And so you add a minimum of ammonia. What's the reaction here? The reaction here is this. You know, silver chloride is soluble or insoluble? It's insoluble, but it's not 100% insoluble. Insoluble just means this. I don't know if anybody reads the little footnotes in the solubility chart. What does insoluble mean? What's the definition of insoluble in our solubility chart? Insoluble in our solubility chart is defined as less than 0.1 moles per liter will dissolve. 0.1 moles per liter, that's quite a lot. And so there are different degrees of insolubility. Well, it turns out silver chloride is highly insoluble. But a tiny bit will dissolve. And it's an ionic compound, so it separates into ion. And so a little bit will dissolve But we could get more to dissolve. How can we get more to dissolve? We could use Le Chatelier's principle. Using Le Chatelier's principle, tell me how to get more silver chloride to dissolve using Le Chatelier's principle. Yeah, I want to get more silver chloride to dissolve. Only a tiny bit, like a micromole will dissolve in a liter. But I want to dissolve the whole thing. How can I dissolve the whole thing using Le Chatelier's principle? I got to keep shifting it to the right. So if I could keep shifting it to the right, I can get the whole thing to dissolve. How? Remove silver ions. How can I remove silver ions? Well, I got to react it with something. I got to react silver ions with something. What does silver ion like to react with? Sulfate? Sulfate? Silver likes to react with bromides and iodides. So you add a bromide or iodide, but the problem with adding bromide or iodide is it makes a new precipitate. Right. Or potentially a new precipitate. And potentially because I gave you that one problem. Did I give you that one problem in week 1? Of what's the driving force? Did I talk about that? If I add I think I did.
What was it?
Look at this as an aside here. And for sure I gave this in Chem 1A. I don't know if I gave this in Chem 1B. I think I gave this as what's the driving force for this metathesis reaction?
What is the driving force?
What is the driving force for this metathesis reaction? A PBT. Okay, so I got a precipitate here of silver bromide. Right? What's the driving force? If I were to reverse this reaction, is there any driving force for the reverse reaction? Because reactions are this competition between the forward and the reverse. Is there a driving force for the reverse reaction? Stronger to weak acid? No, because you guys know about the you should know about the leveling effect. The leveling effect is so these are equivalent. It's a tie. And so the driving force, if we go reverse, will be PBT. And so we have a competition here. The forward reaction precipitates the reverse reaction. Who wins? Who wins? Well, in general, who wins in chemical reactions? Which side wins? Think about it for a second. What is a driving force? Tell me what a driving force is. What is a driving force?
It's like to stabilize like this one.
In general, a driving force, if you were to sum up the 3 driving forces, the metathesis, the redox, the acid base into one sentence, what would that one sentence be?
To go from not stable to stable.
Yeah. And so which one of these is the more stable precipitate? We talked about this, right? Which one should be the more stable precipitate? AgCl, why? Smaller size. So yeah, well, maybe AgCl should be the more stable. However, There's just one problem. And that one problem is this. For heavy metals, heavy metals kind of are what we call soft ions. And really, when we look at bonding, we should be looking at bonding in terms of MO theory. In other words, are these 100% ionic? No, there is some covalent interaction. And that covalent interaction can screw things up because when we're looking at just charge density, we're assuming 100% ionic. And so there is a chance that a soft ion like silver would like a soft anion or softer anion like bromide versus a harder anion like chloride. This is why Lewis, figuring out what makes a good Lewis base is tough. Figuring out what makes a good Lewis base is tough because of HSAB. Right? In general, we can come up with some kind of general guidelines. This is what makes a good Lewis base, But in order to properly define what makes a good Lewis base, we need HSAB, which is what? What was HSAB? Hard soft acid base and MO theory, which HSAB is based on, right? And so that's basically what makes a good Lewis base is tough sometimes because it depends on the covalent interaction in there as well. So sometimes the questions are open-ended, like I don't ask for specifics. I just want to see where people take it. I don't know. Most people don't write HSAB or talk about MO when they're talking about Lewis bases, but sometimes people will throw that in. And so the people who throw it in, because and the people who throw it in there, are they like geniuses necessarily? No, not necessarily. They just, they just remembered it. That's all. And so, but in order to remember, because there's too much stuff to remember, you need that repetition. Right, and so this is actually, if we were to base it just on 100% ionic, silver chloride will be more stable. But if we starting to look at, there's maybe some covalent interaction there, especially with heavy metals, like lead-2 chloride. Lead-2 chloride is more ionic. Lead-4 chloride is actually more covalent. In fact, lead-4 chloride forms PbCl4 molecules, whereas PbCl2 forms an ionic lattice. But lead, there's quite a bit of covalent interaction in there. This is why, the solubility rules, lead-4 chloride is actually soluble in water because those molecules will dissolve in water, whereas lead-2 chloride is insoluble. But anyway, going back to this, there's another way we can tell which one's more stable, and that's based on experimental data. And what type of experimental data could we use to determine which one's more stable? Yeah, what type of experimental data could we use to determine which one is the more stable precipitate, silver chloride or silver bromide? Solubility. Which one? Yeah, in other words, the easy answer to this is which one of these is less soluble. Both are insoluble, but they're different degrees of insolubility. Right? Insoluble just means less than 0.1 moles per liter will dissolve. What we really need is the solubility, which is the maximum amount that will dissolve. And when we compare the solubilities, that'll tell us which side this is favored. And so we compare the solubility of silver chloride with that of silver bromide. But it's not so easy to do because if it were 100% ionic, and heavy metals have this, heavy metals have a lot more covalent interaction in there. And that's why, whereas other species are much more ionic. But, so, if we add something like bromide to attack this, maybe it'll work, maybe it won't. Maybe it'll shift it. So we dissolve the silver chloride, but we end up precipitating out silver bromide. Maybe iodide. Iodide might be even better because iodide should be a softer or harder. Usually heavy metals are thought of as soft ions. And so iodide versus bromide, which one is softer? Iodide's softer, it's bigger, more polarizable. Well, those are the things, it's hard to pick all this stuff up, but the thing that will help you a lot is just, going back and flipping through your notes. And then, not only that, then you have to make all those neural connections so that you can use the information. All these little bits and pieces that we've been talking about. We talked about, I think, everything. It's just putting it together. And sometimes it's difficult to do. Because most people can say, a good Lewis base is an electron pair donor. Then more people, less people will say, there's a good electron pair donor with negative charge density. And then even fewer people will say, well, it's a good electron pair donor with negative charge density, but it's difficult to predict. Sometimes because of, you want to be in that top tier, right? You want to be the person who says, the more detailed answer. A lot of people come up to me and say, is this good enough? My answer? Good enough? Well, I always say, write down as much as you know. But they're always worried about doing that because they might write something wrong, and then I might start deducting because they're writing something wrong. I try not to do that. But no guarantees. On the GRE, I was at this Prometric, place over here on Redondo Beach Boulevard. I didn't know, because when I took the GRE, it was all pencil and paper, but I know, I guess they were admitted. I don't know if the MCAT's taking there too, but I saw somebody was taking the GRE. It's all on the computer. GRE is this exam you have to take for graduate school. But anyway, it doesn't hurt to, if you know it, it doesn't hurt. But you don't want to start making up stuff. If you don't know it, just, okay, leave it off. Just what you feel confident with. Because on the GRE, they penalize you for every wrong answer. A lot of tests, you just guess. But the GRE, you don't necessarily want to guess because you'll lose a quarter of a point. Something like that. Okay, but there's a better way to remove the silver ion. The better way?
Nitrate?
Not nitrate, but it starts with an N, the element nitrogen. Not nitrite. There's something that, like silver ions, and that is ammonia, amine. Amine is a good one for silver ions. And so amine attacks the silver ions, 2 of them, to form this. Well, how do you know 2 of them? Somebody tell me how you know 2 of them attack it. Why not 6? Why not 4? How do you know 2 of them attack it? Huh? And how do you know ammonia like silver? Why doesn't ammonia like lead? Mercury? Well, it could potentially react with those. It does, actually. But it forms the hydroxides and oxides. In this case, silver ions are preferentially attacked. How do you know it's just based on experimental data? This is what's observed, and therefore this is it. We don't know the theory well enough to predict, at least for us right now, to predict this, right? And so we've seen this diamine silver ion before in chapter 24. All right, so what this does is the ammonia attacks the silver ion concentration goes down, thereby Le Chatelier's principle means this is going to shift to the right. And if there's plenty of ammonia around, it'll attack more silver and continue to push this to the right because K is very big for this second reaction. it's not very large, but there's a number, but it's fairly significant. And so this is one way we could dissolve this. Now, the next step here is we can reprecipitate it by adding nitric acid. If we add nitric acid, then we should reprecipitate out silver chloride. How does that work? What does the nitric acid attack? The ammonia. The nitric acid, this is just a regular Bronsted acid base. The nitric acid will neutralize the ammonia and do what? And then if we neutralize the ammonia, it's going to shift this equilibrium to the left and increase the silver ion concentration, which shifts this equilibrium to the left and reprecipitates it. Problem is sometimes people have way too much ammonia and they never get this reprecipitation out because everything gets so dilute that they're starting to work with big beakers at this point. And so we want to do this, then we just want to maximize the amount of precipitate. And so this is what we call separation here and conformation of silver ion. Once we're at the end of this, then what we say is we've tested positive for silver ion. You know, because based on our observations, we must have silver ions present. And I'll tell you, lead and mercury wouldn't have done this. Because there are different chemical reactions with ammonia. Okay. All right, any questions on this? Yeah. And so you just go through the rest of this preparing, you know, what you think you can finish for the day. And then when you come in the lab, you'll just work with your flow chart and try to do those as we go along. Okay, I'm going to stop here and we'll take a break.